In this video, we're going to learn how to solve inequalities involving polynomial expressions. Let's take a look at an example of such an inequality. In this example, we want to solve the inequality x squared is less than 2x plus 3, and we want to solve this inequality for the variable x. Meaning we want to figure out what x values can we plug into this expression so that we end up with a true statement. This is an example of a polynomial inequality because the expressions on either side of the inequality symbol are polynomials. Let's take a moment and see if certain x values are or are not solutions to this inequality. Let's start by asking, is x equals -2 a solution to this inequality? Well, to check, all we have to do is plug in x equals -2 into our expression to see if we have a true statement. So on the left-hand side, we have -2 squared, and this is supposed to be less than 2 times -2 plus 3. All we're doing is replacing the x's here with -2. Now, on the left-hand side, we have 4, and on the right-hand side, 2 times -2 is -4 plus 3. That gives me -1. Is 4 less than -1? No, 4 is not less than -1. That's why we would say that x equals -2 is not a solution to this inequality. Next, let's try x equals 1. Is that a solution to this inequality? So in our inequality, we plug in x equals 1 and see what we get. On the left-hand side, we have 1 squared, and then on the right-hand side, we have 2 times 1 plus 3. Now let's simplify this. On the left-hand side, 1 squared is 1. On the right-hand side, 2 times 1 is 2, plus 3 gives us 5. Here, 1 is less than 5, so this is a true statement, which tells us that x equals 1 is a solution to this inequality. It turns out that oftentimes inequalities have more than one solution. For example, let's check whether or not x equals 2 is a solution. So in my inequality, plug in x equals 2. On the left, we have 2 squared. On the right, we have 2 times 2 plus 3. So that's 4 on the left-hand side. And then on the right-hand side, 2 times 2 is 4, plus 3 gives us 7. Since 4 is less than 7, we can conclude that x equals 2 is a solution to this inequality. So we see here that there are multiple solutions to this inequality. Let's take a look at a graph to help us visualize these solutions. What we're going to do is treat the different sides of this inequality as their own individual functions. So on the left-hand side, we have the x squared function. On the right-hand side, we have the 2x plus 3 function. So this inequality is the same as asking for which input x is the output of the left-hand function smaller than the output of the right-hand function. To help us visualize things, we're going to plot the function on the left-hand side of the inequality and the function on the right-hand side of the inequality. Starting with the left-hand side, we have the x squared function, and on the right-hand side, we have the 2x plus 3 function. So how can these graphs tell us what the solution to this inequality is? Remember that the y values of the points on the graph correspond with the outputs of our functions. Let's look at some of the calculations we've done already. For example, when we plugged in -2 into the x squared function, we got 4. That's why on our graph, we have the point -2, 4 on this x squared graph. And then when we plugged in -2 into the 2x plus 3 function, we ended up with -1. That's why on our graph we have the point -2, 1 on our 2x plus 3 function. Remember that the inequality is asking us when are the outputs to the x squared function smaller than the outputs of the 2x plus 3 function. And this can be interpreted as for which x values are the corresponding y values on the red x squared graph below the corresponding y values on the blue 2x plus 3 graph. Well, when x is -2, my red graph is above my blue graph, so that's why x equals -2 is not a solution. When x is equal to 1, my red graph is below my blue graph. That's why x equals 1 is a solution. Same thing at x equals 2. At x equals 2, my red graph is below my blue graph. That's why x equals 2 is also a solution. So again, if we want to solve this inequality, we want to find all x values for which the red graph is below my blue graph. Looking at our picture here, we see that the red graph starts being below the blue graph at -1, and it keeps on being below the blue graph all the way until I get to x equals 3. So the x values here, the interval from -1 to 3, are the solutions to this inequality. So this here is just a visual representation of what we're looking for when we have polynomial inequalities like this. Now, what we'll want to be able to do is solve these inequalities without having to draw all of these graphs. Now, the first thing we're going to do is move everything to one side of the inequality symbol. And we're also going to call the resulting expression that we have on one side the function f of x. So, for example, let's try to move everything to the left-hand side. So we'll subtract 2x from both sides, and we'll also subtract 3 from both sides. We end up with x squared minus 2x minus 3 on the left-hand side is less than 0. So what we have on that left-hand side, this x squared minus 2x minus 3, that's what we call the function f of x. So our inequality that we have here is now the same as asking for which values of x is our function f of x less than 0 or negative. And to answer this question, we need to know when our function changes signs either from positive to negative or from negative to positive. And that's our second step. We want to find the x values where your function f of x might have a sign change. Now let's take a look at a graph to get a sense of where these sign changes might occur. For example, let's say I have a graph that looks like this. Certain parts of the graph are below the x-axis, which means our function's output is negative there. And certain parts of our graph are above the x-axis, which means our function is positive there. Now let's look at the locations where our function changes signs from positive to negative or vice versa. So it starts off being negative and then it becomes positive. So this location here is where my function had a sign change. If we keep going, our function is positive here, and then as we cross the x-axis, it becomes negative. So this point here is where my function changes signs from positive to negative. Let's keep going. Our function is negative here, and then it switches to positive here. And again, this point right here is where our function had a sign change. Now, all of these locations where we have sign changes, aren't those just the x-intercepts of our function? So from our picture here, we see that a function might have a sign change at the x-intercepts. Now, I say the word might because it's not guaranteed that you'll always have a sign change at an x-intercept. For example, this point at the end here is an x-intercept, but my function before it is positive, and it's positive after it as well. So in our second step here, what we want to do is find the x-intercepts of our function. Now, it turns out there's another way a function can have a sign change. And this is something that we saw when we looked at rational functions. For example, let me draw the graph of a rational function with a vertical asymptote at this dotted line. The graph might look something like this, and then like this. Again, certain parts of this graph are above the x-axis, which means my function is positive there. And certain parts are below the x-axis, which means my function is negative there. And here we see that our function transitions from positive to negative without crossing the x-axis. Instead, the x value where we had this sign change is a vertical asymptote. So a function might have a sign change at vertical asymptotes as well. So not only do we have to find x-intercepts, in step 2, we should also find vertical asymptotes. Now, when we're solving polynomial inequalities, this isn't something that we'll have to worry about since polynomials do not have vertical asymptotes. But in our next video, when we talk about rational inequalities, this will be an important step. So for our example here, let's try to find the x-intercepts. Remember, to find the x-intercepts, what we need to do is set our function equal to 0 and solve for x. So for our problem here, our function is x squared minus 2x minus 3. We want to set this equal to 0 and solve for x. To solve this equation, we're going to try to factor this polynomial on the left-hand side. We'll need two numbers that multiply to -3 and add to -2. Two numbers that multiply to -3 and add to -2 would be -3 and +1. So our function factors as x minus 3 times x plus 1, and this is equal to 0. When we have a product of two things and it equals 0, that tells me that either the first factor equals 0 or the second factor equals 0. So we can split this equation up into x minus 3 equals 0 and x plus 1 equals 0. On the left-hand side, add 3 to both sides, we get x equals 3. And on the right here, the equation x plus 1 equals 0. All we have to do is subtract 1 from both sides. We get x equals -1. So these are my two x-intercepts. X equals -1 and x equals 3. These are the x values where my function might have a sign change. Our last step is to make a sign chart for our function to help us determine the solution. A sign chart is essentially something that we make that tells us what the sign of our function is at each x value. To make a sign chart, we start by drawing a number line. On our number line, we're going to put down the x values where my function might have a sign change. This is what we found in step 2. So here, we're going to put down -1 and 3 on our number line. So keep in mind that my function can only change signs at x equals -1 and x equals 3. Now to fill out this sign chart, what we're going to do is pick x values in each of the intervals that we have on our number line, plug them into the function, and see what sign the output is. Let's start with this leftmost interval here. We want to pick an x value that's in that interval. For example, I can pick something like -2. And what I want to do is take -2, plug it into my function, and see what the output is. So f of -2 would be -2 squared minus 2 times -2 minus 3. If you want, you can type this in your calculator, and you'll see that the output here is 5. Now 5 is a positive number, so on my sign chart, I'm going to draw a positive sign for that interval on the left. Keep in mind that I didn't need to pick -2 specifically. I could have picked something like -3 or -4 or -5 or even -1,000,000. No matter which x value we picked in this leftmost interval, the output of our function will always have the same sign. It'll always be positive because the only places my function can have a sign change are at -1 and at 3. So everywhere on this left-hand side, my function is not going to change signs. It's always going to remain positive. Now let's repeat this process for our middle interval here. My function is not going to change signs anywhere between -1 and 3. So we can pick any x value there, plug it into my function, and see what sign the output is. For example, we can pick something like x equals 0. So evaluate in our function f of 0. This is going to be 0 squared minus 2 times 0 minus 3, which gives us -3. Now, since the output -3 is negative, what I'm going to do is draw a minus sign on this middle interval in our sign chart. So what this tells us is that no matter which x value I picked between -1 and 3, when I plug that x value into my function, the output will always be negative. Lastly, we have the interval on the right-hand side, everything above 3. So let's pick an x value there. For example, we can pick something like 5. Take 5, plug it into your function. F of 5 would be 5 squared minus 2 times 5 minus 3. You can type this into your calculator if you like, and if you do, you end up with the output 12. Now 12 is a positive number, so on this interval, we're going to draw a plus sign. So what this tells us is that for all x values that are above 3, if we plug them into our function, we'll always end up with a positive output. So now we know the sign of our function for every x value. My function is positive for x values less than -1. It's 0 at x equals -1 since it's our x-intercept. It's negative between -1 and 3. It's 0 at x equals 3 because it's another one of our x-intercepts. And then it's positive for x values greater than 3. So now we're ready to answer our question. The question, remember, is for which x values is our function f of x negative? Well, according to our sign chart, our function is negative between -1 and 3. And so the solution to this inequality is the interval -1 to 3. Notice that we have parentheses for the ends of the intervals because we don't want to include the endpoints. At x equals -1, the output is 0. At 3, the output is 0. And since we're only interested in negative outputs, we don't want to include those x values. Notice that the solution that we got here is consistent with the solution that we got when we looked at the visual representation of our inequality on the previous page. Let's try one more example. In our example here, we want to solve the inequality x to the fourth power is greater than or equal to 9x squared. And we want to solve this inequality for the variable x. So let's follow our 3 steps from before. The first thing we want to do is move everything to one side and call the resulting function f of x. So let's move the 9x squared over to the left-hand side by subtracting it from both sides. So subtracting 9x squared, we end up with x to the fourth minus 9x squared is greater than or equal to 0. And what we have on the left-hand side here, x to the fourth minus 9x squared, that's what we'll call the function f of x. Looking at our inequality now, we're essentially asking for which x values is our function f of x greater than or equal to 0? Or another way to phrase it is, when is our function f of x positive or 0? So now let's move on to our second step. What we want to do is find the x values where our function might have a sign change. Again, we might have sign changes at x-intercepts and at vertical asymptotes. Now, since the function we're working with here is not a rational function, we don't have to worry about vertical asymptotes, but we do need to find the x-intercepts. So to find the x-intercepts, we need to set our function equal to 0 and solve for x. So let's set our function x to the fourth minus 9x squared equal to 0 and solve for x. Here we're going to try to factor that polynomial on the left-hand side. Looking at our 2 terms here, we see that there's a common factor of x squared, so let's start by pulling that out. If we pull out an x squared, what's left? Well, removing x squared from x to the fourth, we're still left with x squared. And then from negative 9x squared, if we remove the x squared, we're left with negative 9. Now, this expression, x squared minus 9, is a difference of squares, so we can factor that further. So we end up with x squared times x plus 3 times x minus 3 equals 0. Now, when we have a product of things and it equals 0, that tells me that either the first factor equals 0, or the second factor equals 0, or the third factor equals 0. So this lets us split up our equation into x squared equals 0, x plus 3 equals 0, and x minus 3 equals 0. For x squared equals 0, all we have to do is square root both sides. We get x equals 0. For x plus 3 equals 0, we just subtract 3 from both sides. We get x equals negative 3. And then x minus 3 equals 0. We just add 3 to both sides. We get x equals 3. So my 3 x-intercepts here are 0, negative 3, and 3. Now we're ready for our third step, which is to make a sign chart for our function. To make our sign chart, we start by drawing our number line. And on our number line, we want to place our x-intercepts. So starting with the smallest one, we have negative 3, then 0, and then 3. This divides our number line into 4 different intervals. Keep in mind that these dividers are the only places where my function has a sign change. So everywhere in between, my function will have the same sign. So to make our sign chart, start with this leftmost interval. What we want to do is pick an x value in that interval. So try something like negative 4. Take negative 4, plug that into your function, and determine the output. So f of negative 4 would be negative 4 to the fourth power minus 9 times negative 4 squared. If we type that into our calculators, we end up with 112. So 112 is a positive number, so we'll draw a positive sign on this leftmost interval. Next, let's look at the interval between negative 3 and 0. We can pick an x value here like negative 1. So take negative 1, plug it into your function, and evaluate the output. We have negative 1 to the fourth power minus 9 times negative 1 squared. Evaluating this, we get negative 8. Negative 8 is a negative number, so we're going to draw a minus sign on that interval. Next, let's look at the interval from 0 to 3. We can pick any x value we want in that interval. We can pick something like 2. So take 2, plug it into our function, and see what the output is. F of 2 would be 2 to the 4th power minus 9 times 2 squared. Evaluating this, we end up with negative 20. So again, we're going to draw a minus sign for the interval from 0 to 3. And then we just have one last interval left here from 3 to infinity. Let's pick an x value like 5. Let's take 5, plug it into your function, and see what the output is. We'll have 5 to the 4th power minus 9 times 5 squared. If we plug that into our calculator, we see that the output here is 400. 400 is a positive number, so we're going to draw a plus sign on this interval. Now that we've completed our sign chart, we know what the sign of our function is at every x value. When our x value is less than negative 3, our function is positive. At x equals negative 3, our function is equal to 0 since it's one of our x-intercepts. Between negative 3 and 0, our function is negative. At 0, our function is 0. For x values between 0 and 3, our function is going to be negative there. At x equals 3, our function is 0. And then lastly, for x values greater than 3, our function is going to be positive. So now to answer the question, for which x values is our function f of x positive or 0? What we can do is highlight those positive regions on our sign chart, and this tells us what our solution is. On this left interval, we have the interval from negative infinity to negative 3, and we're going to use a bracket there because we want to include the endpoint, negative 3. Our function is equal to 0 there, and that's something that we want to include in our inequality. For this interval on the right, we'll have an interval notation, bracket 3 to infinity. But that's not all. We're interested in all x values where f of x is positive or 0. We've handled the positive portion. To include all of the x values where my function is equal to 0, we need all of the x-intercepts. We've already included negative 3 and positive 3. We also need to include the x-intercept at 0. So we need to include in our solution and x equals 0. So in this video, we learned how to make sign charts, and we learned how to use them to help us solve polynomial inequalities. I'll also mention that being able to make sign charts is a very important skill to have. It's something that you'll need to be able to do when you take higher level math courses like calculus.